Hello, students. So this video is basically a review of the periodic table. And I know a lot of you are saying, why are you making me watch this? I've already watched basic atomic structure, the periodic table's organization. I just watched, atomic number and mass number and isotopes. Why are you making me watch another video? Well, the reason why I'm having you watch this is the periodic table is critical. It's the best cheat sheet in the world. You're able to use it, and when you understand it, it just makes chemistry so much easier. So I'm going to do a little review, right? So here's a review. Again, left to right, we call those periods. That's why this is here. This would be period 1, period 2, 3, all the way down to 7. So rows are periods. They're also referred to as energy levels, or you can think of them as orbits around the nucleus, orbits where the electrons are occupied. So that's one way it's organized. Then we learned on top of periods, there are what are called groups or families. Those are columns. Remember, those are the alkali metals, group 1A, or alkaline earth metals would be group 2A. And then over here, we have the halogens, which are right next to really what everybody wants to be, group 8A, the noble gases. And that's what this video is going to kind of open up to. But we're going to review the periodic table. And again, these numbers, right, and the symbols we talked about. So if I blow this up, the elemental symbol, typically one capital letter, it may have a second letter lowercase, it might even have a third letter lowercase. So the majority of the time, the first letter is the first letter in the name. So an example, helium, right? The first letter, H, helium, the second letter, lowercase e. Again, people are looking at K, you're crazy. Again, these elements were named before the English language was really common. So it's derived from Latin catrium. The other thing that's important on top of the elemental symbol is the atomic number. The atomic number is what makes this potassium. If I have 19 protons, that's what the atomic number is on potassium. The periodic table is also organized by increasing atomic number. So hydrogen's the first element. Why? It's the simplest element. It has one proton. Its atomic number is number 1. So it's listed first. Then helium is the next simplest element. Why? The atomic number is 2. It has 2 protons. Then we just talked about the atomic mass, how it is a weighted average based on the relative abundance of the isotopes. The isotope's mass is contributed by not just the number of protons, but the number of neutrons, because protons and neutrons are roughly 1 AMU. And if we could take a weighted average, we get the atomic mass in nature. And again, the elemental symbol. So again, the best cheat sheet. And we see it's organized 1, 2, 3, 4, and in sequential order. The other thing that the video showed us earlier was it's organized by 3 types of elements. Metals. Metals are everything to the left of this staircase, except hydrogen. I could put hydrogen right here if I wanted to, right? That would be hydrogen. Some periodic table has it on both sides. Some periodic tables also take the helium and put it over here. And I can talk about that in a minute too. But for the most part, the metals are to the left. So these are all metals. To the right of that staircase, non-metals, right? So here are all my non-metals. That's very powerful, just knowing that. We've already discussed physical and chemical properties. Metals, they're malleable, they're ductile, they're good conductors of heat and electricity, they're shiny, they're lustrous. That's why they're so desirable for jewelry and monetary purposes, right? Non-metals are brittle and dull, right? They're typically low boiling points and melting points. That's why the majority of them are the noble gases, right? Noble gases. Some of them are solids like carbon, graphite, but it's dull and brittle, or phosphorus, right? So you got your carbon right here, and you got your, sulfur and phosphorus, and those are found as solids, but again, they're dull and brittle, they lack luster. And then hugging it, metalloids, they don't know what they are, they're somewhere in the middle. But again, that is very powerful, that organization, knowing if something's a metal or non-metal. Then we talked about different families and how the periodic table was organized based on characteristics of elements that had similar properties, both physical and chemical. So the alkali metals, right, group 1A. Why did these behave the same way? Really, right? So we know the periodic table is organized by the number of protons, right? So remember, carbon has 6, that's its atomic number, it has 6 protons. And we talked about, well, how is carbon, if it has 6 protons, going to be a neutral atom? It's got to have also 6, right? It's got to have 6, oops, I put the number of 6. It's got to have 6 electrons to be neutral, because a 6 plus and a 6 negative makes it a neutral atom. Well, we'll see why alkali metals are in this first group in a moment. But basically, we group them because they have similar physical chemical properties. And even though the periodic table is organized by atomic number, the number of protons, and it's the atomic number, right, that dictates what the atom is, right? The number of protons tells you whether I'm hydrogen, right? So if I have one proton, I'm hydrogen. If I have 2 protons, I'm helium. 3, I'm lithium. 4, beryllium. 5, boron. 6, carbon. 7, nitrogen. 8, protons, oxygen. 9, fluorine. 10, whoops, I was going to write neon, right? And then I go back. 11 is sodium. So the protons tell me what the element is, and it helps organize a periodic table, but really what is critical on its physical and chemical properties, we're going to see are electrons. The number of electrons are going to dictate how these elements behave. So we're going to see that the number of electrons make the alkali metals behave very similar, right? Oop, I went a little crazy. Alkali, that should be alkaline. That's a typo. I'm sorry about that. The alkaline earth metals, group 2A, it's the electrons that make them behave similar. Now the transition metals, this block is right in the center. We're going to get into that in later videos. It's a little bit trickier, so I'm going to hold off on that, but we do know that those are all metals, okay? The noble gases, group 8A. Everybody wants to be noble, right? Everybody wants to be noble. The halogens, group 7A, right? They're extremely reactive nonmetals. Why? They're almost like a noble gas. Basically, everybody wants to be noble. They're all fighting to be noble. They're willing to share electrons because it's just electrons, right? It's the electrons that are going to make these elements happy. It's a number of electrons. And the noble gases have a very happy set of electrons. And everybody's willing to share their electrons, or some elements are willing to lose their electrons, and some are willing to gain to be like a noble gas. So we'll talk about that too. So then we have the lanthanide and the actinide series. And again, just like transition metals, those are for later topics. But I just wanted to go over some basic organization of the periodic table. The other thing I want to mention is, why are noble gases so happy? Why is this group 8A so happy? And earlier I said these elements, right? When I think of chemical reactions, essentially a chemical reaction is breaking bonds and forming new ones. And I talked about that in other videos. So when I break bonds and form new ones, really what I find in a bond is a pair of electrons. So you can think of bonds, right? Bonds as electrons. So when I'm breaking and forming bonds, I'm moving around electrons and shuffling atoms around and make them happy, right? So how are they happy? They want to be a noble gas. Well, what's so special about noble gases? Noble gases are extremely stable. They're unreactive. And that brings us up to the concept of the octet rule. Noble gases typically have 8 valence electrons in their atom. So there's a couple things. I threw out some terminology. Valence electrons. The valence electrons are the electrons in the outer shell. So the way I mean the outer shell is that's what your period tells you. Okay? So if I have hydrogen, right? It has 1 proton, so what does that mean? It has 1 electron. Where does that 1 electron go? Goes in that first shell. If I have helium, right? It has 2 protons, so what does that mean? I have 2 electrons in that first shell, that first energy level, that first orbit. Once I get to lithium that has 3 protons, lithium, right? It has 3 protons, so it has to have 3 electrons. Now there's a problem. That first shell is so close to the nucleus when we go to lithium that it can only fit 2 electrons. So that third electron, there's no more room in that first shell, that first energy level. So where does it have to go? It has to go to the second orbit. And that's why lithium is in the second period or the second energy level. Why? Because you can only fit how many electrons in the first? 1, 2. Once I fill up the first energy level, I have to go to the second. So lithium has 3 electrons, 2 go in the first, 1 go in the second. If I go to beryllium, right? Beryllium has 4 electrons. How do I know? 4 protons. 2 go in the first. There's no more room in that first shell. So now where do I go? The second shell, how many there? 2 electrons. And so on, right? So boron has 5 electrons, right? Boron has 5 electrons. Where are those 5 electrons going to go? Well, here's boron. The first 2 go in the first shell. There's no more room. So where did the other, out of the 5, 2 go in the first, where do the other 3 go? The third. And if we look, this is what the periodic table does for me. It shows me that the outer shell, the valence electrons, the outer shell is what typically where we have the electrons being exchanged. That's where electrons are being transferred, right? So that's what's going to determine electrons and bonding, whether electrons are going to be lost, gained, or shared. It is the electrons in the valence shell, in the outer shell, that dictates its behavior. So what we see is in group 1A, there's 1 valence electron, right? So if I go back to lithium, it had 3 electrons, 2 in the first shell and 1 in the second. So that's why it's in group 1A. It has 1 valence electron right here in the second shell. If I go to beryllium, it's in group 2A. Why? It has 2 valence electrons, so 2 electrons in its outer shell. And they're in the what? Second period. So that's why beryllium's in the second row, second period, that's left to right, and it's in the second column or group because it has 2 valence electrons. So I'm going to jump a bit. I could keep going across and across and across, but basically the way this works is let's look at sodium. Sodium, right? It's got 11 protons. How do I know? If it has 11 protons, because the atomic number is 11, where do the first two electrons, or if it has 11 protons, it has 11 electrons because it's neutral. So where do the first two electrons go? Well, if I count across the periodic table, I have 1, 2 electrons in that first shell. 2 electrons. In the second electron shell, right? So if I drew another, I could have up to 8. How do I know that? So now if I go across right here, period 2, the period represents the energy level or electron shell. In period 2, there's how many? 1, 2, 3, 4, 5, 6, 7, 8 positions. 1, 2, 3, 4, 5, 6, 7, 8. So in the second shell of sodium, there's 8 electrons. Now, if I go 2 plus 8, that's only 10 electrons. But I have 11 protons. I have 1 more electron. Where's that other electron going to go? Well, it can't fit in the second shell anymore. So where does it go? I go further out and I get my next electron in the third shell. So that's why sodium is in the third period as I go left to right, and it's in group 1A. Why is it in group 1A? It has 1 valence electron. So an easy way without me drawing circles, because that's really messy, and I am definitely not a neat person, I apologize. But you could think of it as here's sodium, the nucleus. It's got 11 protons. The first 2 electrons go in the first shell. Why do they go in the first shell? Well, if we look, right, if we look at the periodic table, what do we have? 1, 2 electrons can fit in that first shell. And then 8 go in the second shell. How come? Again, 1, 2, 3, 4, 5, 6, 7, 8. 8 go in the second. Then it has 1 more electron because it has 11. Where does it go? In the third shell, because there's no more room in the second. And there's 1 valence electron. What does that mean? There's 1 electron in the outer orbit for sodium. And that's why it's in group 1A. Just like lithium. Why is lithium in 1A? Well, it has 2 electrons in the first shell, and it has 1 in the second. Why? It's got 3 protons. 3 protons means 3 electrons. Where do the first 2 electrons go? The first 2 electrons go, and I'm really messy, I apologize. Let me just erase all of this, right? The first 2 electrons out of the 3 for lithium go where? 1, 2. That's the first shell, but there's no more room. So where does the third electron go? In the second. That's why lithium is shown in the second period, because that's the outermost orbital of electrons, and it's in group 1A, because it has 1 electron in its outer shell, which we call 8 valence electrons. Now, what makes noble gases so happy? Because noble gases have a complete outer shell that we call an octet. So noble gases are pretty stable. They're unreactive. Why? That's because their outer shell is happy. Now, helium is an exception. Helium is actually a duet. That's because its outer shell, which is the first shell, can only fit 2 electrons. But for the most part, all the other noble gases, because they have more than just 1 shell, which is really close to the nucleus, they can fit 8, and that's the octet. So if I was to look at this, right? If I look at helium, let me erase all this. If I look at helium, I see two electrons. How come? 1, 2. So how can I think of this? Helium has 2 electrons because it has 2 protons, goes in that first shell. Well, what about neon? Well, here's neon. It's got 10 electrons. So how could I think of that? Well, here's neon. The first electron orbit or shell can only fit how many? 1, 2. So there's 2. Now neon's atomic number is 10. So I still have 8 more electrons out of the 10 because 2 go in the first shell. So where do the other 8 go? That's easy. The other 8 go in the second energy level. That's why neon's in where? Period 2, because it has 2 orbitals. How many electrons in the outer shell, the outer orbital, or the valence shell? 8. There's 8 valence electrons in neon. How do I know? Well, I go to period 2, the second shell, which is its outer shell. How do I know that? Because it's in the second period. And I count. There's 1, 2, 3, 4, 5, 6, 7, 8 positions in that second energy level. That's why this is group 8A. Go to argon, right? So argon has how many electrons? Well, if it has 18 protons, because 18 is what makes it argon, it has 18 as an atomic number, which is 18 protons. It's got to have 18 electrons. So the first 2 go where? In that first shell. Again, how come? 1, 2. Well, I still have another 16. 8 go in the next shell. How come? 1, 2, 3, 4, 5, 6, 7, 8. Right? So now I have 10 electrons, but argon's supposed to have 18. So where did the other 8 go? The other 8 go in the next shell. And why 8? 1, 2, 3, 4, 5, 6, 7, 8 in the third shell. That's what the period represents, the third energy level. And it's the valence electrons that gives the characteristics, the physical and chemical properties of these elements, because when atoms come in contact with other atoms, it's the outer shell where the electrons are being exchanged. So that's where electrons are being either shared, gained, or taken. And that's what we call bonds. So the noble gases, because their outer shells are complete, they don't want to do that. Guess what? All the other elements want to be nobility. They want to have their outer shell filled. They want that octet. So that's what the next videos are going to talk about, is what atoms are willing to do to acquire an octet and be noble. We'll see some are willing to share, some are willing to cheat by stealing or just giving them away so that they can be noble. But the periodic table helps us determine whether or not they're going to lose, gain, or share electrons to get that octet based on the distance to the noble gases. And that's what we'll be talking in the next few videos. So I hope you enjoyed it. I hope it makes sense. It's a little bit long-winded, but again, I'd rather give you more than less. And students, again, thanks for tuning in. I appreciate your patience.